It may seem like this moment of inertia quantity of a body necessarily makes problems involving rotating bodies computationally intense, since there are infinitely many possible moments of inertia of a body, one for each possible axis of rotation. It turns out there's a nice theorem that greatly simplifies this dizzying situation, and it's called the parallel axis theorem. It relates the moment of inertia about a body's center of mass, ICN, to the moment of inertia about any other axis parallel to it and a distance d away, which we'll call I sub p. So if we have this ruler plank thing with holes, and its center of mass is here in the center hole, and it's rotating about that center of mass, that would be its moment of inertia for this body and for that rotation axis would be ICM. Well, if we wanted to rotate it around this other one, a distance d away, this is another axis that we could rotate it around. It's not very computationally intense, is what I'm saying, to compute what this moment of inertia would be. So this would be IP, a parallel axis. So parallel axis means these are parallel, right? So it's not just a distance d away and rotated around any axis. It has to be parallel axis and a distance d away that's known. And so our equation, our parallel axis theorem, states that I sub p is equal to I cm plus the mass of the body times d squared. It's pretty simple. And you can search out the proof of this theorem if you're curious, but we will simply be taking it at face value and applying it. So let's do one example. I might as well box this in. Let's do an example. So let's say we have some odd thing here. This part of a mechanical linkage, it calls it, has a mass of 3.6 kilograms. Its moment of inertia, IP, about an axis, 0.15 meters from its center of mass, so that's d, is I sub p equals 0.132 kilogram meter squared. What is the moment of inertia ICM about a parallel axis through the center of mass? So we use the parallel axis theorem. So ICM is equal to IP minus the mass times d squared. Right, it's just rearranged. And if you compute that out, then you get 0.051 kilograms meters squared. Simple as that. So ICM. So it can really save a lot of time, as long as you have a parallel axis. It doesn't matter what the shape of the thing is, you just need the total mass and the distance away. It's quite remarkable. So might as well jot it down. There it is in its regular form there. Because usually you'll have the axis of rotation, or the moment of inertia around the center of mass, and you'll be finding the other one. All right, that's it for this. It's that simple.